Okay. So we were talking about homology, right? So we said that the setup was like this. We start with a d-dimensional simplicial complex that we call delta. And then we make these vector spaces, Ci of delta, where Ci of delta is, we think of as a vector space with bases given by the I-dimensional faces of this guy. Okay. Then we defined these boundary maps last time. We showed that this was that the composition of the boundary of a boundary map and the next one was 0, which means that this is a chain complex, and therefore we have these homology groups. Hi of delta, which is the kernel of delta I mod the image of delta I plus 1. And we said that basically the way we wanted to think about this is that this was kind of like taking these I cycles and modding out by the I boundaries. And the picture that we had is that what lives in here are things like this, a sum of faces that make a cycle. And then the things that we put here are the boundaries of simplices. Okay? So what we're looking for is cycles like this that are not boundaries. Okay? And we were in the middle of doing this example very carefully last time. So we computed one homology group very carefully, right? And this was for this simplicial complex that we keep talking about. We have a full triangle ABC, an empty triangle BCD, and another point E. And so we have this big picture, okay? And I know there's a lot of information in this picture, but this picture summarizes the whole story, okay? So I really want you to stare at this picture and understand it. So last time what we did is that we computed this, right? So we said that the first reduced homology group was one copy of our vector space, and that was because we have this hole right here. Okay? And we actually saw that if we wanted a generator for this first homology group, it was given by BC plus CD plus DB. Okay, so it's going around that cycle. Okay? And then I asked you to compute the other ones on your own and see what you get. And this diagram right here is supposed to summarize the whole computation. Okay? So what is it that I have here? I have my chain complex where I start with this is a two-dimensional complex, so I start with the two-dimensional faces, the one-dimensional faces, the zero-dimensional faces, and the minus one-dimensional faces. Okay? So for example, the space of two-dimensional faces is spanned by the single two-dimensional face, which is the face ABC. Okay? And so that's what I have put right here, ABC. Okay? This is the generator of C2 of delta. And then I have to say what the boundary map does to ABC. Okay? And the boundary of ABC, by definition, is you take off the first letter, and you get minus BC. You take off the second letter, and you get plus AC. You take out the third letter, and you get minus AB. Okay? And so here what I'm describing is the map delta 2, the boundary map, which takes ABC and sends it to BC minus AC, sorry, to minus BC plus AC minus AB. Okay? And so this is really the matrix of delta 2. Okay? Now what about F5? This thing right here is C1 of delta, so this is considered to be the span of the one-dimensional faces, which are AB, AC, BC, BD, and CD. Okay? And these are exactly the guys that I have here. Okay? And these are exactly the guys that I have here. Okay? And here I'm defining for you the boundary map delta 1. So how are you supposed to think about this matrix delta 1? Well, this is the matrix that takes AB, and AB is one of the basis vectors here, right? Because it's one of the faces. It takes AB and it applies the boundary, which says take out the first guy, and you get B with a minus sign. So this is wrong. And then take out B and you get A with a plus sign. Okay? So that means that this is almost right, but the signs are wrong. Okay? And I probably did the same mistake for all of these. So the boundary of AC is A minus C, the boundary of BC is B minus C, the boundary of BD is B minus D, and the boundary of CD is C minus D. Right? So it should look like that. Okay? So this is the matrix delta 1. Then here we have the zero-dimensional faces, which are A, B, C, D, and E. Right? And the map delta 0 just takes each one of these guys into the empty face with a sign of 1. I guess with a sign of negative 1. Because I take out the first guy, and that gives me a minus sign. So really just like this. Okay? And so these are all my vector spaces and my maps, Ci of delta and the boundary maps delta I. Okay. The fact that this is an exact sequence means that if you go from anywhere, and if you map to here, and if you map to here, then you get 0, and then you're just supposed to compute these image mod kernels. Okay? Sorry, kernel mod image. So we did this very, very explicitly in this case. Now, in the other cases, what do we get? Fortunately, Thomas posted this on the forum, and I made a little correction to it, but his argument was basically right. I mean, what you have to do is really just carry out this computation, right? So you're supposed to just take the kernel of this map, mod the image of this map. Okay, so you take the kernel of this matrix. These are the vectors such that the sum of the coordinates is equal to 0. And then you mod out by the image of this thing, and you have to carry out the computation and see what you get. And this is what I asked you guys to do. It's in the forum, so what you get is f to the 1. Okay? And that's supposed to illustrate that there is exactly one hole. Okay? And if you look at the things that live in here, for example, like I said, a generator for this guy is something like BC plus CD minus BD, okay, which means go around here. And if you perform this computation, and again, this is in the forum, you can see it, then you'll see that there are several choices for what your generator is here. But for example, one choice is D minus E. Okay. A different choice is B minus E. But for example, D minus E and B minus E are equal to each other. And why is that? Well, because we're doing this mod the faces, right? And D minus E and B minus E, if you take their difference, that's B minus D, which is a face. Okay? So that means that if you do carefully this computation, you'll see that D minus E is the same vector as B minus E, or C minus E, or A minus E, and those guys generate the homology. So basically what the zeroth homology group does is that it can tell that you have two pieces here in your simplicial complex. This piece right here, and this piece right here. And this is kind of a hole that you can walk through. But what it's saying is that the hole between D and E is the same as the hole between B and E, because it looks like it is, right? Okay. What about here? Well, we're looking right here at the kernel mod the image, right? And again, if you do this carefully, you're going to get that this is also f to the 1. And then if you look at these guys, well, these guys live in these higher dimensions, 2 dimensions, 3 dimensions, 4 dimensions, and there's nothing in this complex, so that means that all of this stuff is 0. But again, it's very important that you look at this computation carefully and that you do it carefully and explicitly and you understand it. And in the homework, you have to do basically the same thing for a different complex. So this would be a good one to check that you understand what's going on here. Okay. So this is kind of the story that we're after here. Okay. All right. So I want to do another example. Boundary of the simplex. Okay. So here's a complex. It's all the subsets of an n-element set except for the whole set. So maybe we can do the example of, and so we call this the boundary of the n simplex. Okay, so this means boundary, and this means n simplex. So for example, what do I get for n equals 2? N equals 3, let's do. So we get all the subsets of 1, 2, 3 except for the whole set, right? So empty 1, 2, 3, 1, 2, 1, 3, 2, 3. Everything except for the whole set 1, 2, 3. If you want to, I'm calling this the n simplex because it is the n simplex. In this case, it's I guess it's the n minus 1 simplex. Because in this case, what is this? Well, it's the boundary of a triangle, right? If you look at a triangle, then this is exactly the boundary of it. You take everything, but the triangle is empty. Now, again, I want to kind of go back between these algebraic and combinatorial arguments into the topology. So if we're topologists for a second, then what we see here is we don't care that this thing has sides or points or anything. We just care about the topological shape. And so for a topologist, this is just a circle. And so we might call this the n minus 1 sphere. That is what we call it. Okay? So this is what we want to compute. We want to compute the homology of this guy. Okay? And so to do that, we basically have to tell that whole story the way that we did it over there. So for example, what are the I-dimensional bases? Well, these are the generators of Ci of delta, right? So span of E sub S such that S is a subset of N, and if my face is I-dimensional, that means that I need I plus 1 elements here. Okay? And so that means that the dimension of C sub I is what? Well, here I have a basis, right? This is a basis. And it's the number of ways of choosing out of a set of n elements, choosing I plus 1 of them. So I have n choose I plus 1 is my dimension. Okay. And maybe we should do it very explicitly here so that you see exactly what we're doing. We're looking at this, right? Okay. Where C2 of delta is the number of two-dimensional faces, and actually there aren't any. So that means that I might as well not put this in the picture. Right? There's no two-dimensional faces here. C1 of delta, how many one-dimensional faces do I have? 3. So this is like F3. How many zero-dimensional faces do I have? 3. And how many zero-dimensional faces do I have? 1. Okay. And so the dimensions that we're seeing here are 1, 3, 3, and we're missing the last number in the row of Pascal's triangle, but these are basically the n-choose i's. Okay. So what does our complex look like? The chain complex looks like this. Let's do that in general. So here we said that the biggest dimension that we have is n minus 2, right? Just like in the case n equals 3, we don't have the two-dimensional triangle. We start with the one-dimensional things. And in general, this is the n minus 1-dimensional simplex, but it's empty. So we have no n minus 1-dimensional faces. We start with the n minus 2-dimensional faces. And so the complex looks like this. Okay. And like I said, this is f to the n choose 0. This is f to the n choose 1, f to the n choose 2. This is f to the n choose n minus 2. And this is f to the n choose n minus 1. Okay. Do you have a question?
Oh, so those, Pascal triangle numbers that only applies when it's n minus 1 sphere. That's for these particular complex.
That's right. So the fact that I get these, these numbers right here, the n choose I, is precisely because of the complex that I'm considering here. It is because we are considering the boundary of the n minus 1 simplex. Sorry, I said n minus 1 simplex, so this is n minus 1. Okay. So because I have this nice simplicial complex, I get nice numbers here. But if we look, for example, at this example over here, well, this was just a simplicial complex that is smaller, but it's not so nice. And so the numbers 1, 5, 5, 1 are just whatever they happen to be. But in this case, they're very nice. They're these numbers right here. They're the binomial coefficients. Okay. Okay, what about these maps? Let me just very quickly draw it in this case, and I think you'll see what happens in general. If I repeat my picture over there, basically, what do I need to do? I need to list over here the 1, 2, 1, 3, 2, 3, 1, 2, 3, right? So I need to tell you what to do to each one-dimensional face. Right? So for example, the boundary of the one-dimensional face 1, 2 is 1 minus 2. The boundary of 1, 3 is 1 minus 3. And the boundary of 2, 3 is 2 minus 3. I think they're okay now. I had them wrong there, and I corrected them there, and I think this is right, yeah. Here I do the same thing. I just have to say where I map each one of these guys. And what I get is just 1, 1. So this is what I get in this case. And I don't know, does this look familiar to you guys? This is very much this. These are exactly the same matrices that we were running into in our first example on syzygies that we did completely. Right? Except they had some letters, right? So here, I think we had x, y, and z. Here we had y minus x, z minus x, and z minus y. But if you forget the letters and you just kept track of the coefficients, this is exactly the same sequence. And in the homework, we did that in class for n equals 3. And in the homework, you had to do it for arbitrary n. And for arbitrary n, you saw that basically this is the picture that emerged. Okay. Question?
This is the negative ones.
Yeah, sorry. These are negative ones. So this is where I have to kind of ask you to recall that we had a very similar chain complex in syzygy land. We had a free resolution like this. It looked very similar, except that if you remember, actually, it didn't stop at n minus 1. Actually, you guys hopefully have your notes of that time, so maybe you can see that we have exactly the same thing. But in this case, we took 3 steps to resolve all the syzygies. We're missing the 3rd step. And in this case, we took we took the next step also. Okay? So actually, what we had was something like this. Okay, and the maps are a tiny bit different. Okay? Here, these are these boundary maps: delta n minus 2, delta n minus 3, it's delta 1, delta 0, and here we have some other maps that I forget what we call them. Maybe this, I don't know. But the point is that if you look at these two things carefully, you'll see that really they're the same thing, okay? And that the argument that we made to show, not only do I have the same dimensions here, but I actually have the same maps, except for these variables that we had on there. Okay? Here we had polynomials, and so the maps had variables attached to them, and here we just have ones and negative ones. But if you forget that, the maps are exactly the same. Okay? And the point of a free resolution is that it's exact, right? And we proved that it was exact. And then the thing is that you can take exactly that proof and repeat it up here, and you're going to see that this is exact. Okay? Because it's basically the same stuff, except maybe with these extra letters that end up not mattering. Okay? And so what we get is that because this guy is exact, this guy is also exact, except that there's one difference, which is that, here I'm exact, so here I'm exact. Here I'm exact, so here I'm exact. Here I'm exact, so here I'm exact. Here I'm exact, but now here I'm not exact, because what does it mean to be exact here? It means that this kernel is equal to this image. And over here, to be exact, would mean that this kernel is equal to this image, but I lost my image. Okay? So basically, I'm going to get that I'm exact everywhere except right here. So you can just imitate the argument. Imitate the free resolution argument. To see that this sequence, this complex is exact everywhere except right here at n minus 2. What happens at n minus 2? What happens is that we get the kernel of delta n minus 2 mod the image of delta n minus 1, but that's the thing that disappeared. This thing disappeared. And so what we get is just the kernel of delta n minus 2. Okay. But again, what we can do is this. We can say, okay, we just need to figure out what the kernel of delta n minus 2 is. But what I'm going to say is this. This map is basically the same as this map. Okay. So the kernel of delta n minus 2 is up to reinterpretation. It's basically the same as the kernel of fn minus 2. And here, this sequence is exact. So I know that the kernel of fn minus 2 is the image of this guy fn minus 1. And what's the image of fn minus 1? Well, this thing is one-dimensional, and I'm mapping it to something. So that means that the image is one-dimensional. And so what I would say here is that basically, if I had something that I don't have here, I mean, if instead of taking my real chain complex, I take this other chain complex, then that other chain complex is going to be exact by the same proof as why this one was exact. And that means that the kernel of delta n minus 2 is going to be the image of delta n minus 1. And the image of delta n minus 1 is just the boundary of this guy. I mean, you should think about when I do this algebraic trick, what am I doing topologically? What I'm saying is my chain complex doesn't have this n minus 1 dimensional face, and I'm kind of like fake adding it. Okay? So in other words, this complex that I take when I go all the way over here, and then instead of going to 0, I come down here, then basically what I'm doing is pretending that this guy is full. Okay? And so what I'm doing here is computing the homology of the full simplex. And what I'm saying is that guy is exact, so there's no homology. And so then I get that the image of delta n minus 1 is the boundary of the simplex, which is exactly my whole, right? So this is f to the 1. And a generator is given by the boundary of the simplex. Okay. So that's the computation. And what that computation does is that it shows basically that if I want to know what the homology groups of the sphere n minus 1 are, then basically almost all of them are 0. The only one that is not 0 is this one. 0 for I different from n minus 2. And here we just get f for I equals n minus 2. Which kind of makes sense because basically we're saying that the n minus 1 sphere has exactly one hole and that hole occurs in dimension n minus 2. Okay. So this is one of our first theorems on homology. Okay, that's the reduced homology of a sphere. Okay. Do you guys have any questions about that? I know that it's going to take staring a while at this to figure out exactly what I said, but I hope you get the general idea of what I'm saying. One thing I should tell you is that, I mean, this is an algebra class, right? So I'm not assuming you guys know topology. I'm about to give you a slightly different proof of the same fact, which is if you know topology, you go another way and it's easier. Here, because we don't know topology, we have to work a little bit harder and look at these diagrams very carefully. Okay. By the way, how can we interpret this thing then? I mean, I don't know. Does this look like a hole to you? A hole between D and E? It could be. But if you think about what does a sphere look like what do spheres look like, right? So what's this sphere that I'm talking about? It's the points in Rn such that the sum of their squares of the coordinates is equal to 1, right? That's our familiar sphere. So for example, if we take S2, well, that's the usual two-dimensional sphere. It's empty, right? What is S1? Well, now that those are the points in the plane such that the sum of the squares is 1, so that's a circle. And what's 0? S0? Well, those are the points on the line such that the sum of the squares is 1. And there's only two such points, which are -1 and 1. Okay. So this is what a sphere looks like. That's why you kind of have to accept that this is a hole. This is a zero-dimensional hole. And that's how we interpret this thing to be. Okay. So I think what I want to do for the rest of the class is just tell you a little bit more about some general facts about topology, because I think I'm kind of shortchanging you if I just give you this definition out of nowhere and I don't tell you anything about it. So I think maybe I'll spend the remaining 20 minutes just placing this definition into kind of where it belongs in topology. So, for example, one thing I want to say is this. I want to say I computed the homology groups of the n-1 dimensional sphere, right? And I found that if I cover this up, right? If I don't tell you what I put in here, maybe I tell you I put a sphere in here, but I don't tell you the dimension of the sphere, but I tell you the homology groups that I got, then from the groups you can tell me what dimension my sphere was, right? And so somehow this is evidence that a one-dimensional sphere is different from a two-dimensional sphere, which, I mean, it's relatively obvious, but you want to prove these kinds of things, right? I mean, you want to have a topological theorem that says that the two-dimensional sphere is not the same as the one-dimensional sphere. And this is the kind of evidence that you can give for that. Okay? So I have to tell you a little bit more about what I mean by the same. And so let's do a little bit of topology. So of course, I have to wave my hands a little bit because I'm not assuming you know topology, but so for example, I'm starting with the word topological space. You might know what that means, or you might not. And if you don't, then you should just think that it's whatever you think a space is. It's a little more subtle than that. It would take us a while to say what it is. So two spaces X and Y are said to be homeomorphic if there is a function that takes the first one to the second one such that. So first thing is that f should be bijective. Okay, Okay, so it's a one-to-one mapping between the points on X and the points in Y. The function should be continuous. And also, if a function is bijective, that means that it has an inverse, right? And the inverse should also be continuous. Okay. So what you should think is that you're deforming X into Y continuously. So this is what we have in mind when we say take a donut and make it a coffee mug, right? So let's do some examples. The square and the circle. Okay. I think you can believe that these two things are homomorphic, right? You can take a square and deform it continuously to make it a circle. What that involves technically is you have to really find a function that takes each point of the square and sends it to a point of the circle. But if you work at it, you can get it. Okay, so these guys are homomorphic. A donut and a mug. Again, you can look for videos of this online. Actually, I just found out if you look up homomorphic on Wikipedia, you're going to get a little video of a donut turning into a mug. You can imagine, right? You take the mug, then you kind of collapse it so that then it looks kind of flat, but it still has the handle, and then you collapse where the coffee was, and you just get the handle. You can do that continuously. Okay? What about this one? The interval from 0 to 1 and the reals. Do you guys think that's homomorphic? Those are homomorphic? Again, depending on how much you know, this might seem crazy because this looks a lot bigger than this, but you guys probably know that it's not, right? That really there are as many reals as there are reals in the 0-1 interval, and the way you prove that is by giving a bijection, and then this bijection is continuous. And what that bijection does, well, that's an exercise for you. You basically kind of, here's the line, here's the segment, and then you basically kind of think of standing very close to here and just kind of projecting it like this. And you take the limit when you get very close. You do something like that. Really, the way you do it is like this, right? You first take the segment and you curve it, so that you can do continuously. So you take your 0-1 segment, you curve it, and now your bijection is going to come from here. I think this is called stereographic projection. So this is how they draw maps, right? Where each point here gets mapped to a point here. So this is P, this is f of P. And that's a continuous bijection. Okay, how about r to the n and r to the m for m different from n? Well, again, you probably know that these guys do have the same number of elements, and there are bijections between them. The question is whether you can make that bijection continuous. That's not such an easy question, and it turns out that the answer is no. How about a point and an n simplex? It's very clear that you can't do that because the point is a single point and the n simplex is not a single point. Okay, so that gives you an idea of what kinds of things are homomorphic, and well, it's not my theorem, but the theorem is that if you are homeomorphic, you have the same homology. If x and y are homomorphic, they have the same homology. Okay. And of course, we're equally interested in the contrapositive, which says that if you don't have the same homology, then you don't get to be equal. So for example, we just proved that the three-dimensional sphere and the five-dimensional sphere are not homomorphic. Okay. But I just claimed in drawing a diagram like this that actually if you look at the n simplex, it has no homology. Right? Because I said that this long sequence that I had here that I curved and made it blue, that was the chain complex of the homology of a simplex. And I said that there was no homology no matter what dimension we're in. Okay? Which in particular means that the n simplex and the point, which is the zero simplex, have the same homology. And yet they're not homomorphic. Okay? So one thing that shows you is that being homeomorphic is stronger than having the same homology. Right? This is an example of two guys that have the same homology, not homeomorphic. But maybe we would like to give another explanation for why these guys have the same homology, and we can. But it takes another definition. So definition, two maps. Let's call them F0 and F1 from a topological space to another one. Are homotopic if here we were thinking of deforming x into y. Here we're thinking of deforming the map F0 into the map F1. Okay. So what I'm going to do is that there needs to be a continuous map from U cross. So I'll tell you in a second what I mean by this. So basically what I'm saying here is that for every number between 0 and 1, I have a map from U to V. Okay? So you should think that this is kind of like a time variable, right? So what I have is a map from U to V that is changing with time. So for example, when the time is 0, then this should just be the 0 map. Okay? When time is 1, you should have the 1 map. And then in between, for every number between 0 and 1, you have to define some map from U to V. And you have to do it in such a way that this is continuous. Okay? So the map is transforming continuously. Okay? So let's see an example of this. I'm going to consider two maps from, say, just the unit ball to the unit ball. So this is just the ball, the two-dimensional ball. Okay. You see what I mean by that? It's just the full circle with center 0 and with center at the origin and radius 1. I'm going to define two maps. Okay. The first map is just going to be the identity. And the second map is going to be as far from the identity as possible. Everything goes to the origin. Okay. So I'd like to claim that these two maps are homotopic, which you might find surprising because they're very different from each other. Okay. But what I'm saying is that I can kind of think of continuous maps. So for every time t, I need a map. And I need it so that as t varies, the map is continuous. The map varies continuously. And the map starts being this, and the map ends up being this. And to give you a hint, I'm going to switch these two. Of course, that doesn't change anything. So the first one's going to be 0. Everything goes to 0. And the second one, everything stays still. Can you guys think of what this should be? It should just be dilate by t. Of course, because t is between 0 and 1, that means that that dilation just makes it smaller, and you stay inside the circle. So this is a map from the ball to the ball, and under any reasonable definition of continuous, this must be continuous. Like I said, that you have to check what does it mean to be continuous, but this is continuous. Okay. So these two maps are homotopic. Okay. And now we're going to say that topological spaces x and y are homotopy equivalent if there are forward and backward maps. So there's a map from x to y and a map from y to x such that if you go from x to y and back, so that's so when you take the composition of these maps, so for example, f composed with g, that takes you from from y to y, right? And so this map from y to y should be homotopic to the identity from y to y. And this guy goes from x to x, and this guy should be homotopic to the identity map in x. Okay. So that's some condition called homotopy equivalence. Okay. And again, let's do an example of this. Let's prove that this guy, a two-dimensional ball, and the point are homotopy equivalent. So how do I do this? I have to define maps from x to y and from y to x. Okay. Think about it, we're not going to have a lot of choice here, right? Because we need to send every element of x to something, and y only has one element. So we have to send it there. And we're going to take y, it only has one element, which we're calling 0. And we need to map it to somewhere, and probably the natural thing might be just to map it to the center. Center of the circle. And so what do I need to check? I need to check what happens if I take f composed with g. Okay. So g takes, so this goes from y to y, right? So it takes 0 to 0 to 0. So f composed g is actually the identity in y. And what does G composed with F do? Well, that goes from x to x. It sends x to 0 and 0 to 0. So it sends everything to the origin. And we just saw that this map that takes anything and sends it to the center is homotopic to the identity. Okay, we just saw that here. And so that means that the two-dimensional ball and the point are homotopic to each other. And the same argument works to say that the n-dimensional ball and the point are homotopic to each other. And as you can imagine, the point is that this theorem is also true for homotopies. Homotopy equivalent. So if two spaces are homotopy equivalent, then they have the same homology. Okay? So what does that mean? Well, it means that instead of doing that long sequence for the n simplex, right, if we want to find the homology of the full simplex, we say, well, the full simplex is homomorphic to the full ball. The full ball is homotopic to the point. And that means that the full simplex has the same homology as the point. And instead of doing these crazy exact sequences up there, I just have to compute the homology of a point, and that takes me maybe a couple of minutes to figure out what that means. But this very powerful theorem allows you to shorten your computations a lot. Okay? And so in practice, when you compute these things, you do want to kind of combine topology and algebra and combinatorics. So that gives you just an idea of kind of how the field goes. And now we're going back to combinatorics. And so next time we'll talk more about homology groups, and we'll see what they have to do with these Fourier solutions. All right. Do you guys have any questions? The full n-dimensional simplex is homotopic to the point, but it's not homeomorphic. So this doesn't explain why they have the same homology, but the homotopy equivalence does explain it. And that's a better explanation than going through all these sequences and just finding that everything cancels out.